Okay, our first section, chapter 4, 4.1. We're going to look at the graphs of the sine and cosine functions. All right, most of our trig functions, their graphs are periodic functions, meaning the same picture just keeps duplicating over and over and over again. So there's a predictable pattern. And it's just not trig functions. I mean, if I do like an EKG on my heart or something, they can see my heartbeat. It's beep, 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 or whatever, right? So it takes on that same pattern. So you see something go up, down, and flat, and then repeats up, down, flat, up, down, hopefully not staying flat, right? All right, so our sine and cosine graphs are periodic. We're going to see how they have a shape, not like this one, but a repeating shape over and over. So let's look at this basic function, sine x. So the sine function, f of x is equal to sine x. I told you in the past, I usually like to, instead of using x's and y's, I like to use always a Greek letter for my angle. So you may see sometimes I write this, f of theta is equal to the sine of theta. Both means the same thing. This specifically, you know, what is your angle? X in this case, right? And then the output of that. So let's list a bunch of ordered pairs. So you can graph anything, right? Start picking values for x. See what comes out. Well, x is an angle, so I want to pick those nice angles that we know of. So let's start off with x and f of x. And let's just use like quadrant 1 for right now. 0. My next angle, I'm going to put this all in terms of radians. Pi over 6, pi over 4, pi over 3, and let's just end it at 90. I'm at pi over 2. All right, so you might want to use your unit circle if you wish, that's fine. But if I'm looking at 0, my order pair at 0 is 1, 0, right? Sine value is the y on the unit circle. So that's 0. Pi over 6. That's the square root of 3 over 2 and 1/2. That evaluates to 1/2. Sine of pi over 4. Square root of 2 over 2. Sine of pi over 3. Square root of 3 over 2. And the sine of pi over 2 is 1. All right, so that's quadrant 1. All right. Let's look at quadrant 2. All right, next now past 90 or pi over 2, we reach 2 pi over 3. And then we'd have 3 pi over 4, 5 pi over 6. And now we're at 180, which is at pi. Now all in quadrant 2. I can use all these reference angles to get the same values for the sine of these angles. So 2 pi over 3 is reference angle is pi over 3. It'll be a square root of 3 over 2. We're in quadrant 2. Sine is positive, right, in quadrant 2. So all these values, outputs will be positive here. So the pi over 4 reference is square root of 2 over 2. Pi over 6 reference, that's 1/2. And the pi, your quadrantal, your y value is 0. All right, continue on quadrant 3. Quadrant 3, you would get to 7 pi over 6 first, and then 5 pi over 4, and then to 4 pi over 3, and then to 3 pi over 2. Same thing we just did over here. It's always going to be these same exact values, but just now we're in quadrant 3. Everything will be negative, those values. So sine of a pi over 6, reference angle is 1/2, but now we take the negative. Square root of 2 over 2, negative. Square root of 3 over 2, negative. And then 3 pi over 2 is one of your quadrantals, so that means what is the y coordinate? -1, right? And lastly, quadrant 4. Next, we'd run into 5 pi over 3, and then the 7 pi over 4, then 11 pi over 6, and back at 0, which is also 2 pi. Again, everything in quadrant 4 is negative, right? And at 2 pi is same as 0, so it's evaluates to 0. 5 pi over 3 is reference pi over 3, so it's the square root of 3 over 2, sine of that. Square root of 2 over 2, and that makes a -1. So we got all our trig function values. You can do it this way, pretty simple without even having to worry about the unit circle. Notice I just looked at quadrant 1, a couple of points in there, and I got everything else with the other quadrants. Same values, just now positives and negatives. All right, so let's plot all this. So our function, we've got a bunch of ordered pairs. All right, we're going from 0 to 2 pi, right? So that's all the numbers I have that I'll list on here. All right, so I'm gonna try to draw this as best to scale as possible. If 2 pi is right here, half of 2 pi is pi, right? So about midway would be pi. Half of pi, pi over 2. Midway between pi and 2 pi is 3 pi over 2. All right, next I have to put in the pi over 4s. That's half of pi over 2, right? So that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. This is 7 pi over 4. Let's do pi over 3s. So a third of the way would be, let's see, about right here, I guess. And 2/3 of the way would be about right there. So that's pi over 3. And then this is 2 pi over 3. Same over here, split this up into about thirds. Be about right there and about right there. This is your 4 pi over 3, and this is your 5 pi over 3. Let's see if I got some room to put in the pi over 6s. Well, pi over 3, half of that is pi over 6, right? So let's put in a different color, about purple. So in quadrant 1, we got pi over 6, quadrant 2, we got 5 pi over 6, which is about right here, just right before pi. Next, we have 7 pi over 6, right after pi. And then quadrant 4 is 11 pi over 6. All right, so now we start plotting. Notice in our table, nothing is larger than 1 or less than -1, right? So that's our highest y value and our lowest y value. So let's just plot 1 here and 1 there. Now, the scaling on x and y are a little bit differently. They're not exactly the same as far as units. The tick marks representing. So pi is 3.14, so a third of that would be about 1. So pretty close enough, that's good. All right, so now go back and start plotting. Well, you might not say, I know exactly what a square root of 2 over 2 looks like. Use your calculator, I can tell you that square root of 2 over 2 is about 0.707. Square root of 3 over 2, you should know that, recognize that as about 0.866. So now all we do is plot these ordered pairs and connect the dots. 0 is 0, 0, right? Pi over 6 was 1/2. Pi over 4 is 0.707, so maybe about there. Pi over 3 is 0.866, about right there. Pi over 2 is 1. 2 pi over 3 is 0.866. 3 pi over 4, 0.707. 5 pi over 6, 1/2. So you see what's happening. That pi is at 0, right? So we got this nice kind of arch. I'm trying to do my best to connect the dots, which I'm missing. So that covers quadrants 1 and 2. Everything in quadrants 1 and 2 are positive, right? All our y values are above the x-axis. They're positive y values. When you go to 3 and 4, those y values are now negative. So 7 pi over 6, we are negative 1/2. 5 pi over 4, negative 0.707. 4 pi over 3, negative 0.866. 3 pi over 2, negative 1. 5 pi over 3, 0.866. 7 pi over 4, 0.707. 11 pi over 6, 1/2. 2 pi back at 0. So this is 1 period for your sine x. Is equal to 2 pi units. So this picture starts duplicating. As I go over now past 11 pi over 6 to 12 pi over 6, now 13 pi over 6, and so forth, right? Now we're just going repeating the unit circle again, just more than one revolution. You would have the same exact picture. Just going on and on and on and on and on in both directions. So a nice sine wave. So the sine function starts off at the origin and starts increasing. So you're going up the roller coaster first, right? And then you drop down, and then you go up, and then you drop down. So it's just a roller coaster ride. All right, some properties. The domain for this function. You say it's going on and on and on forever and ever and ever, right? So it's coming from negative infinity towards positive infinity. The range. or the outputs, right? What can the outputs be? In this case, never anything smaller than -1 or bigger than +1. Can include them, so I'll use brackets if I use interval notation, -1 all the way up to +1. It's periodic, every 2 pi units. What about the intercepts? Specifically the x-intercepts right now. Right. At integer values of pi, or multiples of values of pi, right? So look, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, -1 pi. So negative pi, 0 pi, 2 pi, ... right? Coming from both directions. So I could say integer multiples of pi. Sometimes they say n times pi is where your x-intercepts occur. Has symmetry. So it's symmetric with respect to, all right, let's look at it. If I say to the x-axis, means they would have a point directly above and below that would match up. That's not the case. It's the y-axis. They would have a point directly right and left that would match up. That's not the case. But there is a point directly through the origin where if I had a point, say, a comma b, then -a, -b is on the graph. So if I choose opposite x's, I would generate opposite y values. So this is symmetry with respect to the origin. When you have that type of symmetry, this says that the function is an odd function. Meaning, if I take the cosine of a negative angle, I get I'm sorry, not cosine, we're talking about sine here, right? Sorry. The sine of a negative angle will generate the negative of the sine of a positive angle. All right, so that's your basic sine graph. All right, next we're going to look at the cosine graph. It's very, very similar to this because you know sines and cosine graphs, their outputs, where their trig function values, they're all in this form of 1/2, square root of 3 over 2, square root of 2 over 2. They're the same values, now just for different angles, right? So the cosine function, f of x is equal to the cosine of x, or might use theta sometimes. So you might see f of theta is equal to the cosine of theta. Right, so I'm not going to list everything around the unit circle again. Let's just look at quadrant 1 in the quadrantials. So if I have x and f of x, start off with 0. And again, think about your unit circle if you need to relate to that. Your cosine value on the unit circle is your x coordinate. So the x coordinate at 0 is 1. Pi over 6 would be a square root of 3 over 2. Pi over 4, square root of 2 over 2. Pi over 3, your 1/2. Pi over 2 is 0. And then let's go to just pi next. So x coordinate there, -1. 3 pi over 2, back at 0, and at 2 pi, it is back at 1. All right, so when I plot this still over 2 pi, half of that is at pi, half of that is pi over 2, 3 pi over 2. We know we go as high as 1, as low as -1. Pi over 4, right there. Pi over 6 right here, and pi over 3 right there. All right, so at 0, the value is 1. Let's put it in red. Pi over 6, 0.866. Pi over 4, 0.707. Pi over 3 is 1/2. Pi over 2, 0. And then at pi, we're at -1. Then at 3 pi at 0. And then we're up here at 1. So if I connect the dots, it's supposed to be a nice smooth curve, just like it was with the sine graph. So do that. It's not a straight line. So it comes down to a minimum right there, and then turns around, goes back up. This is terrible. Let me see if I can connect my dots better than that. Do a thicker pin. There we go. All right, so if you miss the dot, just make the dot bigger, right? There you go. So that is your cosine graph. This is f of x is equal to cosine of x. And it goes on forever, right? So this pattern would keep on going like that and like that, on and on forever. Still with the same period of 2 pi. And you say the period of 2 pi is because that's when you make that full revolution around the unit circle, you start hitting those same exact coterminal angles now. All right, so some properties of this one. The domain is still all reals, negative infinity to positive infinity. The range, same thing as the sine graph, from -1 to +1. It's periodic every 2 pi units. The x-intercepts. These are at pi over 2, 3 pi over 2. If you keep on going, see the pattern. 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so forth. All as well as their negatives. All over 2. So these are odd multiples of pi over 2. And then the symmetry of the graph. It's not the x-axis. Again, a point on the bottom would match with a point on the top, directly above it. But a point on the right matches exactly with a point on the left of the y-axis, right? So this is symmetry with respect to the y-axis. So this tells you the function is even. So if a function is even, it tells me that if a comma b is on the graph, then its opposite x value creates the same y value. So if I have a cosine of a negative angle, a negative x value, it creates the same as the cosine of that positive angle. Pretty good? Again, you can put these in the calculator too, just to verify it. You ever forget that, oh, I don't remember which one starts off high or whatever, or low at the origin. Just put in here y equals, and let's clear that out, sine x, sine of x. And then one unique feature on this graphing calculator too, you don't have to worry about adjusting window dimensions. You hit zoom, option 7, trig, Z trig, and it's gonna put it on the right scaling for you. So usually it shows you from negative 2 pi to positive 2 pi. Okay, so you get 2 periods drawn on here. So that's your sine wave. Mode, I'm in radian mode to see that. If I was in degree mode, let's see what kind of picture I would get. Zoom trig again, I get the same picture. As long as you hit that zoom trig button, it knows, so hey, I'm dealing with, if you're in radians, I'm in radians, I'll see the radian values along the x-axis and it'll adjust it. If not, it'll put degrees on the x-axis. Right now I'm in degrees. See how my window is from negative 352.5 positive 352.5, where if I go back to radians, my window gets adjusted when I go back and hit zoom trig. So there's negative 6.15 plus a negative 6.28, negative 2 pi. And you can play around with this too. You can zoom in and out, changing dimensions if you want to see other parts. But an easy way to double check if you're looking at a sine graph or a cosine graph. All right, what if I change it up? Make it a little bit more complicated than just sine x or cosine x. Let's put some numbers, some coefficients in front of that trig function. So if I have, let's do the sine, say f of x is equal to, let's say 3 times the sine of x. What does this do? Before we had just 1 times the sine of x. Where we saw 1 at? In the range, right? High is 1, low is negative 1. So if I have 3 here, that's going to indicate my range as well. This is called the amplitude. So 3 is the amplitude of the function. How high and how low will it go from the x-axis? How high? How high and how low will it be from a horizontal line passing through the middle of the graph? I don't want to say the x-axis because eventually we're going to shift our graphs away from the x-axis. So how far and how low will it be from the middle horizontal line of the graph? So we usually denote it with this notation. You might see f of x is equal to a times sine of x. A is the amplitude, absolute value of a, that is. In this case, I had a positive number, so the amplitude is that positive number. So if I want a quick sketch of this graph, it's the same exact graph of the sine wave. So you just draw that. You list their key points. Their key points are their intercepts and the highs and the lows. So 2 pi is an intercept, pi is an intercept. The high point is midway. between 0 and pi, and the other low point is midway right there. So the period hasn't changed. It's still 2 pi, right? But the graph goes as high as 3 and as low as -3. That's it. Same picture. If you were drawing on the same scaling as just f of x equals sine x, yeah, then you see how it got stretched higher and lower. But we don't need to worry about that. We're just concerned about the numbers, x and y axis. All right, so the range is going to equal, in this case, from -3 to +3. Or if I'm looking at this right here, the amplitude is going to go from, say, a negative little a to a positive little a, or the amplitude equals to that. Questions so far? These are pretty straightforward, right? Everybody by this point knows how to graph something just by plot pointing, right? That's all we're doing. I could have did the same thing and see how picking values for x and then multiplying it by that. It just stretches your y in that direction. But if I put a number in front of the x, so if I have, say, let's do the sine of 4x. Y equals sine 4x. So we have an amplitude of 1, right? So the absolute value of the coefficient of the trig function is just 1. This 4 right here is going to affect the period. In f of x equal just sine x, we had amplitude of 1 because the coefficient is 1, and we had a period of 2 pi because the coefficient was 1. So 2 pi divided by 1 is 2 pi. That's how we got that period. So now over here, for y equals sine 4x, the period is going to be 2 pi divided by 4, which is pi over 2. So if we put the coefficient, this is going to either shrink our period or extend it wider. All right, so quick graph of that. Over one period of pi over 2, I'm going to list the key points. Half of it, half of pi over 2 is pi over 4. Half of that is pi over 8. So now between pi over 4 and pi over 2, this is easy to figure out instead of doing any arithmetic, just count it. Here's 1 pi over 8, there's 2 pi over 8, and in between would be 3 pi over 8. So whenever you're dealing with the fractional values, that's the easy way to get your key points. 1 of these, 2 of these, 3 of these. Our amplitude is 1. High as 1, as low as -1. Our sine starts at the origin, goes uphill, ride that roller coaster to the top of the first key point. Intercept. Down to the bottom. Minimum key point, back up right there. let's graph f of x is equal to -2 times the cosine of 2/3 x. So let's just identify some important information. The amplitude is going to be the absolute value of -2. It's 2, right? The period for cosine was periodic every 2 pi, just like sine was, right? So it repeats itself every cycle of 2 pi units. So it's 2 pi divided by the coefficient of that x, 2/3, which is 2 pi times the reciprocal, 3/2. That cancels, that's just 3 pi. What does the negative do? So all it does is if I didn't have that negative, say x is equal to 2, plug it in, we get a y value out, say, I don't know, +8, I don't know, this is just hypothetical. But now if I say put negative of that function, I just get this opposite value. So my y value just negates. So if I generated positive y's, now I'm generating negative y's. So instead of going up, now I go down. So all it does is does a horizontal flip along that middle line, right? Our middle line in this case is just the x-axis for this, right? So all right, so we have enough information to graph this. So our period, that's not too horizontal. Let's fix that. It's 3 pi. Half of 3 pi is 3 pi divided by 2. Right? So don't make this as complicated as it needs to be when trying to figure out what these key points is. So half of this one, now half of that one. Half of 3 pi over 2 is just multiplying by half. You get 3 pi over 4. So this is 3 pi over 4. This is 6 pi over 4. This is going to be 9 pi over 4. All right. So all you're doing is just multiplying this first one by 3, right? Get it over here. All right, so we have an amplitude of 2. Sine graph starts off at the origin. It normally goes uphill to that peak, but we know since that negative in there, we have to reverse everything, right? So if you want, you can draw it all in like this, and then put your final graph to be the mirror image of that, which would be this. So that's one period. I didn't tell you to graph over a certain number of periods, but if you wanted to continue on, say if I said over 2 periods, instead of keeping it going to the right, I can also go to the left, right? That shows another period. Because I already have all these numbers positive to the right of the origin, I just list all those same numbers negative to the left, and I've got all those same key points, right? So if you wanted to go over one more period, I would have -3 pi over 4, -3 pi over 2, -9 pi over 4, and -3 pi. I just continue on, high point, intercept, low point, back to an intercept. All right, so the formatting for this we've seen is f of x is equal to a times some trig function, sine or cosine, of x, well, b times x, that is. Absolute value of a is the amplitude. And the period is equal to 2 pi divided by b. Split up the period into 4 sections. Into 4 intervals to denote where maximum and minimum and intercepts occur. All right, let me give you some practice. Try this. See if you can come up with a sketch in your key points. Y is equal to -3 times the cosine of pi times x over 1 period. Key points listed. All right, so we have an amplitude of 3, right? And the period 2 pi divided by pi just leaves 2. Oh, nice numbers to work with, right? So don't even have to worry about fractional values in terms of pi. All right, so we're up. High is 3, low is -3. Period of 2. Key points, half of that is 1, half of that is 1/2. Over here, 3 times 1/2 is 3/2. It's a cosine graph, but the negative of that cosine, so I'm gonna have a flip around it. So instead of starting off high over here and working down like this, it's gonna flip this around the x-axis, so spin around here. We will start down here, go up like that. And then there. So that is your y is equal to -3 cosine of pi over x. Why is my battery running low? I'm not plugged in. Hold on. All right, what if I do take the same equation? Y is equal to -3 times the cosine of pi x plus 3. What does this plus 3 do? Well, the amplitude is going to stay. You can say the same exact picture, except now we just push it up, right? So instead of, let's put it in, say, blue right here. This would just shift every point that you see up 3 units. So everything goes up 3. So you basically are looking now at going from 0 to 6 instead of -3 to +3. So I have to go 1, 2, 3 up here. So follow that same picture. Like that. So it changes my range, right? So the +3 shifts 3 units up. So the range went from -3 to +3, now to 0 to 6. What if I gave you the graph and asked you to give me the equation? So I think we're actually pretty easy. If I give you, let's say, this graph, all right, just from the graph is easy to tell where the amplitude and period is, right? And then the shape of the graph, you can tell, is it a sine graph or a cosine graph? That's a cosine graph, right? Cosine graphs don't start at the origin. They start either high or start low. But since this one's starting low, it got flipped, right? So this is cosine graph, negated, has a amplitude equal to 2 and a period of 4 pi. All right, so I want to write it as an equation, either f of x or y equals either one, it doesn't matter. So y is equal to the negative of 2 times the cosine. We need to figure out what is beta. It's a half. Just guessing or calculating? Right. So the period is determined by 2 pi divided by b, right? Well, we know the period is equal to 4 pi. You solve that for b, you can see how b would equal to 2 pi divided by 4 pi. Pi's cancel out, 2/4, 1/2. Right? So b is 1/2. So this is 1/2 times your x. And I don't have any horizontal, any vertical shifts, nothing up or down, right? So that's good to go. All right, I could also ask you a question like this. Suppose given function f of x is equal to negative 12.8 times the sine of 82x minus 74. Describe everything compared to f of x equals sine x. So I don't want you to graph that. You can do it, right? It's just your numbers are just ugly, right? But we would have a sine graph that gets flipped with an amplitude of 12.8, a vertical shift downward 74 units, and a period of 2 pi divided by 82, right? So you didn't think you'd have an essay problem in a math class, right? This is one of the times that I do put a problem like this on the test, and I'm looking for those specific things. Usually I have it like list. Okay. So we'll list everything out. Number one, the amplitude is equal to 12.8. Not negative, the amplitude is always positive. Take the absolute value of that. Number two, we have a horizontal flip. Now it doesn't have to be all in this order, right? Where it occurs, I'm not too concerned about that just now. We'll figure those out later. I don't need the equation of a horizontal line, but it just flips. Not along the x-axis because it shifts downward. $74 units. And the last thing I can say is the period is now 2 pi over 82p and reduces to pi over 41, right? All right, so as a recap, f of x is equal to a times some trig function. I'll just put it like this. Of bx, and then I can do something here inside it, plus or minus some c in front of the argument. Not in front of it, inside the argument, that is. And then plus or minus some d. So the a tells me my amplitude. The trig function right now is just sines and cosines. B tells me how the period is adjusted. And then plus or minus the c right here, we'll look at this next time. This is going to be a horizontal compression or a shift. Think of it that way, or a stretch. So it's actually just going to change and adjust the graph in that period. And then the plus or minus the d, that's your vertical, up or down, right? So this horizontal shifts. This is your vertical shifts. B, used to find period. And A is your amplitude. Absolute value of A is. So an example may be in the form, say f of x is equal to -3 times the sine of 5x plus 4 minus 1. So we'll look at this and we can do that same thing. We're going to still have a sine graph that gets flipped horizontally, right, because of the negative, with an amplitude of 3 units and a vertical shift down 1 unit, and the period is going to be changing, right? So 2 pi over v, and then there will be a horizontal shift 4 units, in this case to the left. That's a lot of information just in there, but we still have all that. You can graph it by hand or with a calculator. So that's 4.1. So right here, that last part's a little bit of introduction to 4.2. When we're going to look at more translations, that's what that's called, all that movement, left, right, up and down of the graphs. We'll get more detail about that. All right, any questions? Yeah, we'll do this all this with tangent, all the graphs, secant, and all that stuff. But same format basically. You'll still see the shifts.